essay is titled Malaria Drug Resistance Risk in HIV. So this is generally an intersection between machine learning and comedy. So the main question we have here is, can you predict when anti-malaria treatment will fail in patients that are also living with HIV/AIDS? So here's what we are going to cover today. We have the introduction, we shall walk through the related works, problem statement, right through the research questions, objectives and contributions, walk you through the architecture, dataset description, model selection, results, conclusions, and then the limitation and the acknowledgement. So anti-malaria treatment failure prediction is difficult, especially in clinical areas where we have limited resources, we don't have enough funding, we don't have enough equipment to record the data. So we end up having data that is actually not labeled. And so we can't predict, we can't know if this malaria will fail or not because we don't have enough data to know that. And so what we have come up with is a predictive risk scoring model, which determines the World Health Organization clinical staging for patients using physiological biomarker data. So, but the major problem, as I said, we are facing is that most of our data is not labeled because we are majorly looking at sub-Saharan Africa and Uganda. So most of the data that we got is not labeled, meaning that there was not a formal doctor that sat down and recorded this data. So because of that, we won't be using deep learning models because these ones will overfit the small tabular medical data sets, and so we shall lack the interpretability. Instead, we're going to use tree-based ensembles which handle nonlinear biomarker relationships better and provide clear feature encoding. And so, because of that, we're going to get data that is easily interpretable by any clinician, and it will be easy to know, it will be easy to interpret and understand that the outcome that has come out of our model. Yeah, and so this model is also going to be optimized for low compute deployment in resource limited clinical settings, meaning even in areas where we don't have much, it's going to work best here. So moving on to the next, so what does current research do? Studies continuously show that there is a high burden of malaria and HIV infection in the sub-Saharan parts of Africa, especially Uganda. So when this HIV a patient is going to weaken their immunity generally, and so it's going to make their body open to any parasite that wants to come in, and they're going to be increasing the parasite density. And because of that, we're going to see that these anti-malaria treatments are going to be failing because of the parasite density in our patients. And so we also see that those CD4 count, which is an immune health marker, shows that wherever in our data set we have this low CD4 count, and so we see that wherever we have a low CD4 count, it's going to correspond to a high failure risk. So we have SCTs like AL and DP, and that are really effective in HIV positive patients. So DP has lower rates of failing. Then the ARTs that we are giving our HIV patients, some of these are actually influencing the rate of failure in our patients because they're going to increase the lumefantrine levels, for example, and so it's going to lead to a high risk of failure in our patients. So moving on to our next slide. What deploying our models is that we have to be labels fasting and the risk of manifold distortion. So time geometry is a highly complete tabular data set. Meaning most of them, 75%, don't have ground truth. So when we use the preprocessing, like local median or mean imputation, the variance of the feature space artificially collapses. So the subsequent dimensionality reduction and pseudoneighbor propagation will fail catastrophically because we're going to see that we are going to end up assigning we're going to end up assigning patients to groups they don't belong to. We shall see that high risk minority patient will be assigned to majority average class. So that's why this is a very big problem. Then this optimization failure occurs because median imputation destroys the true topology. And so it forces the semi-spotlight algorithm to interpolate across an artificial dense center rather than the true physiological distribution. So that's why we end up deploying a robust multivariate iterative reputation, for example, in source, which is a beta for manifold projection, and the architecture will propagate systematically with a bias. So this will be our beta choice to go with. So continuing with our slide. Come to our research question. We have questions that relate to how does CD4 count correlate with the anti-malaria treatment failure in our data sets? When we have a low CD4 count, we also have a low failure rate and vice versa. And which anti-malaria drug treatment is most effective in HIV immunotide? Where the HIV prevalence indicators also show high malaria drug resistance failure. And also, if patients with weak immune systems, if we have patients with weak immune systems, do we need to move them quickly to stronger backup treatments? So these are the questions that are driving our objectives for this research. So what did we actually do? We developed a predictive model, a predictive failure risk, as a need to calculate our CD4 counts with the regional resistance markers, and then we quantify how specific immune types directly correlate with malaria treatment, and build a drug effectiveness map to identify first which treatments maintain the highest clearance rate in the presence of HIV. And we have a geography overlapping map to kind of thing that we're going to map high risk overlap zones by linking regional HIV prevalence with localized data on sulfadoxine, pyrimethamine, and hyperacine resistance to specify where clinicians face the highest problems. And then we propose assist to help HIV positive patients get the right medicine faster. So moving on, we are going to look at the architecture of our model. Yeah, we have our methodology where we're going to input the body patient data 25 and the body 25. And then we are going to train our Gaussian process classifier, get the raw prediction probabilities, calibrate them, and then use the calibrated probabilities to get the high confidence selector, and then we generate the pseudo label, add pseudo label data to training state, and then we get the final trained model improved with improved predictions on clinical data. So there are some stages where we have to go back, retrain, and then others where we have to make decisions and do that. So this process is somewhat iterative. Yeah, so this is the architecture we used, and so I'm going to pass on the audience to my groupmate to continue the rest of the work. Thank you so much.
Hello everyone, my name is Alho Prisma and I will be taking us through the dataset description and exploratory data analysis, our selection of a model and deployment. So our dataset contains hematological biomarkers, which use that is the CD4, the hemoglobin, the white blood cell count, which I use to predict World Health Organization HIV clinical stages. So the major challenge that we face is that 75% of our data is unlabeled, meaning most of the patient records have no confirmed diagnosis. Because of this, a normal trend split would be very unreliable. So we opted to use a ground truth only test split and reserved 20% of our only physician labeled data for evaluation and used the rest for semi-supervised training. So this ensures that our results reflect real clinical performance and not just the model agreeing with itself. And then we look at our EDA. So we explored the data visually and confirmed that CD4 count is strongly correlated with disease severity. And patients in advanced World Health Organization stages have significantly lower CD4 counts. We also observed high variance in biomarkers like hemoglobin and platelet counts across immune tiers, which confirms these features only carry predictive signal for our model. Then we look at our model selection and deployment. So the model that we selected is a self-training with Gaussian process classifier. And why we selected it is because its accuracy is the highest of the 12 models that we evaluated. Its accuracy is 0.94. It has an F1 score of 0.912. And we also evaluated its explainable AI results with sharp and permutation importance. So this model captures complex relationships in biomedical features and produces well-labeled predictions. So we have seen that it natively supports semi-supervised learning. It can learn from both labeled and unlabeled data, which is perfect since we have 75% of our data is unlabeled. It uses a Gaussian process, which produces calibrated probability estimates. And third, we run an XAI audit using sharp and permutation importance to confirm the model's decisions to be interpretable. And this is critical for clinical use. Then we look at the architecture of our selected model. First, we have a raw data set, then we put it through feature scaling to normalize its data. Then we train our best classifier. In this case, our best classifier is the GPC, the Gaussian process classifier. Then we predict unlabeled samples, select high confidence predictions, add pseudo labels, retrain the model, and then final predictions. Thereby retraining, we are doing an iteration. So this architecture works in iterations. Our model starts by training on small labeled sets, then predicts labels that are called pseudo labels. It adds the most confident pseudo labeled samples back into training and repeats. So each cycle improves the decision boundary, and Miss Forest imputation is applied beforehand to preserve the true structure of our biomarker data. Then we look at our output results, comparing the label spreading with self-training GPC. So we compared our model against label spreading, which is a common semi-supervised baseline. And in this case, we see that self-training with GPC clearly outperforms label spreading. And the results hold on our ground truth only test set, which means the model generalizes to real and seen patient data, not just the data it's to the labeled itself. This validates both our model choice and evaluation strategy. Then we move to our model selection and deployment interfaces. In this case, we are going to see that we have a Streamlit web application for predicting HIV malaria therapeutic efficacy, and it classifies cases as active, which is 1, or not active, which is 0, using a self-training GPC trained on combined clinical data. So it works as follows. Our user opens a URL that is provided after running our app.py in the IDE, in this case, Visual Studio Code, which opens the Streamlit app in the browser. The app has 3 tabs. This is the single prediction, the batch prediction, and model evaluation. In this case, we are going to look at the single prediction and how it works. So single prediction, the user inputs patient biomarkers manually, clicks predict, and the system runs and gives a prediction label that is active or not active. Then we also have a confidence score, a probability from the GPCs, and an automatic clinician flag if confidence falls below 75%. But using the single prediction would be hectic since we are entering values manually and we have very many records in our data set. So better that we use the batch prediction where you just enter our data set and the app predicts all at once. So our IP assets in this case are going to be our trained model, which is the self-training gpc.joblib that we had saved in our IDE, a standard scalar that captures trained data distribution, which is scalar.joblib, an ordered featured schema that ensures column alignment to prevent shape mismatches, which is the feature columns.joblib. So failure to have our ordered featured schema would mean that we are going to have, maybe our app is not going to run correctly, or we are going to have features, but they're not going to be exactly identical to the ones that we have in our data set, which is very important that we have our feature columns, the job lib. So we also have the Streamlit clinical interface with 3 tabs after running the app.py in our Visual Studio Code. Thank you so much.
Hello everyone, this is Arije Docas, and I'll be taking you through the conclusions and limitations. So here we begin with a key limitation of our architecture. Our model relies on the initial distribution of just 25% of the labeled ground truth data. If that small labeled set has any demographic or socioeconomic bias, say most patients come from one region or income level, then the semi-supervised process can accidentally amplify those biases across the larger unlabeled dataset. This hurts what we call out of distribution generalization, meaning the model might fail when applied to patients from different backgrounds. To counter this, we are open sourcing all imputation scripts, pseudo-label thresholds, and hyperparameters. We also fix random seeds so that every training run is deterministic and auditable. So what we did, we framed the antimalarial treatment failure prediction from a simple statistical task into a disciplined, semi-supervised classification problem. We explicitly addressed the mathematical risk of manifold distortion. That's when poor imputation collapses data variance. By using robust methods like Miss Forest before pseudo-labeling, we enforced calibrated pseudo-label propagation to avoid semantic drift and optimized everything for edge compute, meaning it can run on modest hardware in resource-limited clinics. The result is a mathematically defensible and clinically triage tool. Next steps. Looking ahead, first we will validate our model on recent global datasets from 2021 to 2024 to ensure it still works as parasite resistance evolves. Second, we plan to integrate genomic markers like piperacin and sulfadoxine pyrimethamine resistance to improve accuracy. Third, we will expand semi-supervised learning to tap into even more unlabeled clinical data. Recommendations, we also offer several recommendations. We use semi-supervised learning more broadly to reduce labeling burdens. Prioritize research on moderate and severe immune tires where treatment failure risk is highest. We enhance the feature engineering for hemoglobin, white blood cells, and platelets. Improve predictive modeling specifically for high-risk immunocompromised patients. And finally, integrate these model findings into public health policy and treatment guidelines. I want to close by thanking my supervisor, Mr. Galwango Marvin from the Department of Computer Science at Makerere University for this invaluable guidance and technical mentorship. And thank you to Makerere University for providing the academic environment and platform to present this work. Thank you.